Hello and welcome to my video, lesson 6.1 on the fundamental counting principle. So in this lesson, we're just beginning to talk about perms and coms in 30-1. And we're going to start off with this simple and interesting question. How many ways can 2 t-shirts and 5 pants be arranged to make an outfit? So we're starting off with this simple question. I hope you enjoy my nerdy t-shirts that I put there. Hopefully you guys get the joke. So we're combining somehow the t-shirts and pants here. And so what we're going to do is we're trying to make an outfit. Now, every outfit can have 1 shirt and 1 pair of pants. You're not going to wear 2 pants at the same time, and you're not going to wear 2 t-shirts at the same time. That makes no sense. So what we're going to do is we're going to just think about this. If we have this red t-shirt chosen, then we have 1, 2, 3, 4, 5 options, right? 1 per pair of pants. If we have this blue t-shirt chosen, we have 1, 2, 3, 4, 5 options. You could count it up. And because there's 5 and 5, we have 10 options. Now, when we do this, when we're talking about this in terms of a question, this is a pretty simple question. 2 and 5, really simple. But how are we going to do this in general? What we're going to do is the fundamental counting principle. And the fundamental counting principle is simply a way of helping guide your answer. And it's basically just a fill in the blanks question that you create for yourself. So you say, you've got the shirt category, you've got the pants category. How many different ways can we choose a t-shirt? Well, there are 2 versions, so we put a 2 there. Then we ask how many different ways can we choose a pair of pants? Well, there are 5 options there, so we just multiply those and we get 10. Which hopefully makes sense because you can see that the purple option, there were 5 options, plus the green option, there were 5 options. And so we just added those together to get the 10. But if we can generalize this, if we add another t-shirt, oh, that's not working very well. If we add another t-shirt, then how many more options do we add? We add another 5 options, right? And so every time we add a t-shirt, we're just adding another 5, and if you add the same number over and over again, that just means multiplying. And so that's why we do this, and this is called the fundamental counting principle. Okay, so we're going to go ahead and do some different interesting examples. So here is a D&D example. In the board game D&D, people roll a variety of different dice, not just the normal 6-sided dice. So this is what a 6-sided dice looks like. We call this a D6, but you can have any other interesting sided dice, like a D12, a D20, a D4. D4 is kind of interesting. It's like, what side is the right side? Like, what side is the one that counts? Well, it's the side with the thing pointing up, so it's actually this 3. It's not actually a side, it's a vertex, which is kind of interesting. But anyways, I digress. So this is D&D. So if you were to roll both D10s, and there's a reason why we do this, how many different versions of that throw exist? Well, how do? We set this up. So we do D10 from 0 to 90, and D10 from 0 to 9. And how many different options are there? Well, there's 10 sides. So it's 10 times 10, and it's 100, which makes sense because the 1 is in the tens position. How many different options in the tens position? And then the other one is in the units position or ones position. So we put those together when we want to get a percent in D&D, for example. Okay. If you were to roll a D12 and a D8, how many versions exist now? I recommend you pause the video, and see if you can do this yourself. Okay, D8, D12. It's as simple as 8 times 12, which is 80 plus 16, so 96. So, which version had more options? Well, 10 times 10 was bigger than 8 times 12, even though 8 plus 12 is 20 and 10 plus 10 is 20. We're multiplying here, and so the 2d10s has more options. Okay. We can put some restrictions on variables by limiting some options. For example, in D&D, there may be an ability that lets you rethrow if you get a number less than 5 on the D20. So if you roll 2 D20s, what are the possible outcomes with and without that restriction? So if we roll 2 D20s, by default, or like normally, it would be 20 times 20, and it'd be 400. Okay, but now we're going to compare that to the restricted version, so D20 with restriction. And now we cannot have a 1, 2, 3, 4, or 5. So that means there are 15 options. So 150 plus 75, so 225. So obviously, without that restriction, it's actually more options. All right, let's look at part D. Mr. Trigger played D&D at one time for about a year or so. On his worst day of the adventure, he rolled 3 1s from a D20 in a row. I seem to have incredibly bad luck when it comes to games with luck. So, if the probability is determined by putting the chosen outcomes or favorable outcomes, which is what we normally talk about in 30-2, over the total outcomes, then what is the probability of rolling 3 1s in a row? Well, the chosen outcomes are 1, 1, 1. Like there's only one option. Like it's rolling a 1, then rolling 1, rolling 1. So that one is 1. We're really asking about the total outcomes. So if we have 3 blanks, what are the total number of options? Well, it's 20 times 20 times 20. It's 8,000. So what was the probability? 1 over 8,000. So 1 over 100 is like 1% chance. This was significantly lower than 1%. It was less than 0.1%. It's very unlikely. So there's my answer. Not great. If you wanted to, you could actually divide this like that. Or if you wanted in percent, it would be like this. So pretty bad outcome there to roll 3 1s in a row. Okay, let's talk about credit cards or passwords and PINs. So when coming up with a PIN for a credit card, they require a simple 4-digit number. Let's assume that these are only numbers, not letters, and that any number can be used. How many different PINs are possible? Well, we're just going to have 4 fill in the blanks. Now we could use the numbers from 0 all the way to 9. So this has 10 options, 10 options, 10 options, 10 options. Okay, so it's not bad. 1 with 4 zeros after. So it's 10,000 different options. So not that bad. But what if they say now that numbers cannot be repeated? And a lot of people follow this rule. So if you're trying to guess someone's PIN, this is probably a fair rule to follow. So let's do this again. There's still 4 digits. We start with 10 options. But now we've removed an option. We've decreased the number of options by 1 because we've used up a number. Then we've done it again, and then we've done it again. That's 720 times 7, I think. So 5,040. And just by adding that one little restriction, seems like little, we've basically halved our number of options. Now what's really crazy is a lot of people use much more simple pins, like 1, 2, 3, 4, or their year of birth. And so if you think about year of birth, well, you can just go 19, and then, so the first two are picked, and then we can just guess 2 more digits. Well, that's not too hard. Or you could be in 20 and then guess the next 2 digits. And again, that's not that hard. So keeping that in mind, there are ways you can guess this a lot more easily. Okay, in some places like Switzerland, they mandate 6-digit PIN requirements. How does this compare to our previous answer? Well, now with 6 digits, it's 10 times 10 times 10 times 10 times 10 times 10. So it's 1 with 6 zeros after. Well, look at that. 1 million different pins that can be used. So this changes things quite drastically compared to 10,000. Okay, but now what's an interesting option, and I don't know if there's anywhere in the world that allows this, but what if we allowed 4, which we got, 5, or 6? Okay, well, let's just think this through. Let's try the 5 first. So it'd be 10 times 10 times 10 times 10 times 10. 5 times, so this is 100,000. But if we were to put 4, 5, or 6, and that or is really interesting and important. If we say or, that means we're going to be adding. So we're going to say this number, and this number added together because it could be 4-digit or 5-digit or 6-digit. And so when we add those together, we get this result. Even better than Switzerland. But is it better enough? Maybe not. I don't know. Maybe Switzerland's onto something. Just adding another digit is just maybe just the better idea. Otherwise, some people will choose 4-digit numbers. Okay, so the key that I want to point out here is when we say the word or means adding. Okay, whereas over here, I want to point out that and means multiplying. Okay, so and means multiplying, or means adding. Okay, so for Windows 10 and 11, they request that I also use a short pin. I think this is ridiculous, so I choose to add letters to extend the length, because on digital platforms, it's much easier to actually just randomly guess until you get a password. So I added letters and extended the length. I'll tell you that my pin is longer than 6 digits, but that's fine. We're just going to assume that I use a 6-digit length with letters and numbers. So if it's letters and numbers, how do we change this? Well, it's going to be 1, 2, 3, 4, 5, 6. But each digit could be a number or a letter. So it's 10 plus 26 because there's 10 numbers, 0 to 9, and 26 letters, A to Z. So it's letters or number in this position. And again, or means adding. So that's why we're adding. So 36, 36, 36, 36, 36. So that means each digit, and I have 6 of these, could be a letter or a number. And the point is, just even turning that on adds security. Whether or not you actually do all of those. How many is this? 1, 2, 3, 4, 5, 6. The point is, even if you don't do all of those letters, and some of them are numbers, or all of them are numbers, you've added complexity just by having that requirement, or that ability to have that requirement. So making that change, even if you stick with numbers, is always a good idea. So yeah, what is this going to be? 2 billion, 2.1 billion. It's a very big number. Okay, last question we're going to take a look at. Determine the number of distinguishable 5-letter arrangements, doesn't have to be a word, that can be made using the letters from the word friend. Note that you can't use the same letter from the word more than once, and that the word distinguishable means the implication that every arrangement looks different from every other arrangement. So determine the number of 5-letter arrangements if any letter can be used anywhere. Well, this basically means no restrictions. So 1, 2, 3, 4, 5. How many options are there? 1, 2, 3, 4, 5, 6. So 6 options. But once you've used a letter, you can't reuse it. So now there's 5 options, 4 options, 3, 2 options. So putting that all together, we can just go ahead and type this in. 6, 5, 4, 3, 2, and we get 720. Okay, if the word must use R as the last letter, when we recreate this, there are still 5 spots, but R must be here. So there's no other option for that spot. So that is a 1. So what we can do is look at the rest of the letters. Well, if we've used R already, now we have 5 options. 4, 3, 2. So we've decreased our options here. So if this is 6 times 20, so 120. Okay. Part C is a little bit more difficult. The word must contain an E. So what we're saying here is that there must be an E somewhere in the arrangement. How do we decide that? Well, I'm going to suggest that the best way of doing this is actually to think about it without the E. So what if we just do the total number of options, which was this one, but we subtract by the option that was not favorable, like not the one that we wanted. So what if we do not E as an option? So then we'll have 5 different choices because it's F, R, I, N, D. And so it'll be 5, 4, 3, 2, 1. So it's 120. But those are the ones that don't have E, so we want one with E. So what we're going to do is go 720 minus 120, and we're going to get 600. And this is the number of options that has an E. Okay, and then our last option is going to be middle letters must be consonants. Is that going to be too complicated? Yeah, this is going to be too complicated. We're going to do we're going to change this. We're going to say the first and last must be vowels. This is going to be much more simple. The other one is possible, but it's going to be too complicated. So we're going to say this is a vowel. This is a vowel here. So we can have a vowel that would be an I or an E. So it could go here. Or once we've chosen that, then it has to go here, the other one. Then we can look at how many letters are left over. 1, 2, 3, 4. So there's 4 options left. Then a 3, then a 2. And so you just have to look at the restrictions and kind of follow the rules. And so this is going to be 12 times 4, 48. All right. I hope this video helps you better understand the idea of fundamental counting principle in a number of different simple ways. And good luck.